Hello everyone, welcome back to the Vehicle Setup Bootcamp series. This is episode number 4 and today we'll look at anti-roll bars and wheel alignment. First we'll go through the basics of weight transfer for a car and try to understand how the wheels get loaded based on the car's stiffness. We'll then have a basic overview of camber and toe for the tires of the car. So, based on our flowchart, it is evident that the aerodynamic balance of the car has been fixed, and now we'll focus on optimizing the mechanical balance of the car to maintain an optimal compromise between agility and stability. First, let's consider a car as shown here. The black dot at the center of the vehicle represents the center of gravity of the vehicle. This means that lateral forces will effectively act on this point. The red and blue dots placed at the front and rear of the vehicle respectively represent the front and rear roll centers of the car. A roll center is basically the effective point about which the chassis of the car rolls at a specific instant. What I've shown here are the roll centers in static condition. Based on the kinematics of the suspension components of the vehicle, this roll center tends to change its position dynamically as the car goes through the corner. If we look at the front view, we can see that the roll centers for the front and rear suspension assemblies need not necessarily be at the same height from the ground. Looking at the isometric view, we can see that the ideal roll center positions must be on the XZ plane of the car, but this also heavily depends on the symmetry of the suspension design. Most of the time, apart from oval racing, a symmetric design is preferred. Now, let's have a look at the forces acting on the car to understand the importance of these centers. Assume the car is at the apex of a corner. As seen in the previous videos, we can see that the forces acting at the front CG and rear CG summatively form a yaw moment about the effective center of gravity of the vehicle. The longitudinal placement of the CG of the car determines the orientation of the yaw moment created and thereby results in either oversteer or understeer. The key point to remember from this is that if the effective inertial weight of the car is biased to one end of the car, that end of the car is more likely to be the first to reach its tire saturation point and lose grip. Now, when we consider body roll, you will see that this weight bias can also happen between the left and right tires individually as well. Let's assume that the effective roll center of the car is this purple dot here. The car doesn't roll above the center of gravity, at least not entirely, and this is because of the nature of suspension systems. Car suspensions always comprise of moving components, linkages, and compliance. Adding to this, the car also basically pivots above the tire contact patches, so an effective instantaneous center of rotation exists, similar to how an instantaneous center of rotation exists for a vehicle when it yaws through a corner. So here, let's assume the static roll center is at a height of HCR as shown. The word static is important here as the roll center dynamically changes as the car changes its orientation. Now, when the car takes a corner, the centripetal force acts at the center of gravity and the outside tire gets loaded. Or in other terms, there is more normal force on the outer tire. The roll moment created by this lateral inertial load transfer is this equation here, where the moment is taken above the roll center. Now, there are two types of load transfer occurring here. The first one is elastic load transfer, which is the inertial moment divided by the track width of the vehicle. The second type of load transfer is that which occurs due to the change in the geometry. And this is basically because the roll center is not stationary and also rolls above the contact patch of the outer tire, thereby resulting in this equation here. An important point to note here is that since the roll center of the car changes as the car rolls, the orientation of the wheel also changes. And we'll see this in the next section of this video. Chassis roll is generally undesirable as it compounds to the effects of compliance and results in a less responsive car. Now, let's consider a car that's in the middle of the corner. The chassis tends to roll outwards, thereby loading the outer tire. This green bar seen here is an anti-roll bar or a torsion bar. This basically stores potential energy when it gets twisted. When the chassis takes a right turn, it rolls to its left side in the direction of travel and thereby presses down the left side of the anti-roll bar while lifting the right end up. Assuming the tires are in contact with the ground, the linkages on them don't move. As a result, reaction torque is developed, trying to push the roll bar back to its original position, thereby pressing the outer wheel down even more. Think of it this way. When you lean on a wall with your hands, you load that hand. But when you resist and push away from the wall, it adds an additional normal load at that hand. Basically, this is Newton's second law. So, this means that apart from the load the chassis puts on the wheel due to roll, an additional load is exerted on the outer wheel, since both wheels are essentially connected together by the anti-roll bar. This is a concept that is initially difficult to visualize and may feel counterintuitive, but if you spend some time with the math, it starts to make sense. Note that the total load on all 4 tires combined is still the same. Mass isn't magically appearing out of nowhere. Instead, you're distributing the load between the right and left tire. Note that the difference in load between the left and right tires is higher in the case of the anti-roll bar equipped case. This may be good to an extent as the cornering stiffness of the outer tire is higher due to more load, but can also lead to loss in grip at higher speeds. Now, let's look at this concept with some numbers. Assume you have a car with 50-50 load distribution with 5000 newtons on each wheel. When the body rolls into a corner without an anti-roll bar, let's assume 500 newtons from each inner tire gets transferred to the outer tires. Now, let's add anti-roll bars of equal stiffness to the front and rear of the car. Let's assume this removes an additional 500 newtons from each inner tire and sends it to its corresponding outer tire. Now, what if the front anti-roll bar is stiffer than the rear? Well, in that case, less load is transferred from the rear inner tire to the rear outer tire as compared to the load transfer from the front inner tire to the front outer tire. So, the difference in grip levels is higher in the front than the rear, resulting in potential understeer. The exact opposite effect can be observed on the flip side with the stiffer rear end as compared to the front. So here we've got a McLaren P1 with 2 different setups on stage 1 of the Nürburgring Nordschleife. So we now head downhill through the first series of bends. As you can already see, the understeering setup is using all of the track and riding the curbs. The oversteering setup slightly lacking in pace, just to a bit of compromised exit at the corners. As we now enter a heavy braking zone while turning in, and the understeering car is just marginally more stable and planted into the corner. We go through this next series of corners. Not much to say here, both cars seem to be neck and neck. And as you can see, the understeering car surprisingly kicks inwards as it hits the curb. Quite unusual behavior there. I think I may have accidentally hit a bump that I couldn't see. So we now continue flying down this track. Not much to say here. Both cars seem to be level in terms of performance. They're very gradual corners. No real sudden inputs to steering. As we hit this curb, you can see that the oversteering car is getting really twitchy. That's the problem with having a stiff rear end. If you hit that curb and you press the throttle way too much, you're definitely going to have a potential to spin out. As you now fly down to my favorite section of this track, we're going to fly down this straight, gear up for a very fast left-hander, and a big moment there from the understeering car, almost went right into the grass. Now the oversteering car is caught up, nearly binning the left setup into the gravel trap over there. Now both cars are neck and neck as we go under this bridge down this straight. We're now gearing up for the final section of this stage. These are quite generic corners, nothing much to say here. Both cars again seem to be performing at the same level. And now we gear up for a heavy braking zone as we enter the chicane sequence. And this is where you see a huge difference in performance. At the entrance, both cars seem to have the same entry line. But at this exit, you see that the oversteering cars just lost the rear end nearly. And that's the main issue with having a very stiff rear end. So as you can see, there's no right or wrong setup in this type of track with a mix of all types of corners. It depends on your driving style and how much you want to conserve either the front or rear tire. Generally, you want to have a bit of oversteer for the sake of agility, but since many circuit cars are rear wheel driven, you may end up with limited traction on the rear. So when we look at this performance distribution, you can see that a stiffer front and rear setup tends to result in a highly responsive car at the cost of vehicle stability. Softer setups tend to be more driver friendly but may not be suitable for tracks with multiple chains of corners. If you use a stiffer rear anti-roll bar, you get an oversteering car, which works well for very technical tracks like Monaco. A stiffer front ARB gives you more understeer and works better to neutralize oversteering aerodynamic setups. It is also suitable for super speedways and tracks with long gradual corners. Now, let's quickly go through one more concept which is related to chassis roll and suspension, and that is wheel alignment. The first parameter we look at is camber. This is basically the angle made by the rotational plane of the tire with the vertical when viewed from the front. So right now this car has neutral camber. When the top of the tire leans inwards, it's referred to as negative camber. Note that sometimes the angle is taken to be negative by default, which means that when someone says they're adding camber to the wheel, it's generally understood as adding negative camber. However, this is not always the case, so do be wary of that. Now, in reality, the tire won't simply lift off the road. In fact, the contact patch actually gets skewed, as you can see here. Because of this constant skew being present as the tire rolls forward, a lateral force is generated, and this is called camber thrust. Think of this as a sort of slip angle scenario, but from the front view. So having camber provides a level of straight line stability to the car, but its most important effect is seen in corners. When the car rolls into a corner, you can see that the suspension geometry moves and thereby changes the roll center position. This also affects the alignment of the tire, and you can see that the inner tire is way more negative than the outer tire. In this case, the less loaded tire has more slip and can potentially lead to loss in grip. However, this setup also gives high turn-in, so the car tends to be very responsive. If you have a neutral camber setup to begin with, you can see that the outer tire goes into a positive camber as the car rolls, thereby acting against the cornering force and reduces the cornering ability. This is why generally cars are run with negative camber. So let's start a lap around Watkins Glen. We fly down the main straight to the first braking zone. As we turn in, both cars stick to similar lines, and right off the bat you can see that the negative camber car is much more responsive but gets quite twitchy mid-corner. We now head uphill through turns 2, 3 and 4, and you can see both cars evenly matched, with the negative camber helping the car on the left just flow through the section better. We fly down the straight, and this is where the neutral cambered car has better acceleration and gains the advantage. We now go into the chicane sequence, and the cambered setup is using its agility to gain time and catch up with the neutral setup. We take this long right-hander gearing up for another straight, and the neutral setup just launches ahead with almost no tire scrub to stop it. You now take the final 2 corners, and let's just see whether the cambered car can catch up. Well, it certainly closed the gap once again, but just not quite there as we get onto the main straight to complete a lap around the Glen, with the neutral car finishing nearly 1 second ahead, as you can see here. So this just shows that camber tires can actually help in cornering but compromise on straight line performance of the car. If you view the vehicle from the top view, the alignment of the tire with respect to the center line of the car determines the toe value. When the tires point inwards, it's called toe in. As you can see, this gives the tire a constant slip angle while moving in a straight line, but also causes the tires to scrub against the road, which affects its straight line speed. In the toe out scenario, the tire forces act outwards. Without getting into details of steering systems and geometries, let's see what happens when the tires are turned. In the first case, you can see that the outer loaded tire has a greater slip generated, which suits its functionality. In the second case, however, the inner less loaded tire has high slip generated, which may provide good turn-in initially, but can also result in loss in front-end grip, thereby causing understeer. However, these effects are exaggerated, and toe is better used for straight line stability and tire heating in long straights. Here you can see the effect on top speed as the setup with neutral toe easily hits a higher speed around the Daytona Superspeedway. With that, we reached the end of this episode. I hope this one was informative and that you've got a better visual understanding of dynamic effects in corners. The next episode will focus on controlling the torque output of the vehicle using an amazing piece of automotive technology, the differential. We'll also have a look at final drive ratios and gearing. The next episode will also be the final technical segment in the Vehicle Setup Bootcamp series, and after that I'm planning on creating a video where I'll set up a vehicle from scratch to make it more interesting for you all. Which car and track combination would you like to see? Let me know in the comments section below. With that, I'd like to thank you for your time, and until next time, take care. This is Saidat signing off.